You know, usually when we talk about math, there is this expectation of absolute precision.
Oh, totally.
Like it feels like engineering, right? A 5 is always a 5. You count 5 physical bricks, you have 5 physical bricks. It is solid, unchanging.
Right, and it's comforting, honestly. We like our numbers to be these concrete, fixed realities that we can just rely on.
But then you step into the world of percentages and suddenly those solid bricks just like turn into water. They just take the shape of whatever container you happen to pour them into.
Yeah, they really do.
So welcome to the deep dive. Today, we are on a mission to totally demystify percent and percent change.
Which is definitely needed.
We have got an incredible stack of material in front of us today. We're looking at everything from your TEAS and HESI A2 nursing entrance exams, study notes, to historical texts on actuarial science, and even some really eye-opening clinical research papers.
There's a lot of ground to cover.
Yeah, so whether you are currently pulling your hair out, prepping for those nursing exams, or, you just want to avoid getting duped by tricky statistics in the news, this deep dive is going to change how you see numbers forever.
Because the way we casually throw around percentages in everyday life, it completely masks just how slippery they actually are mathematically. I mean, they are shapeshifters.
They really are. So let's unpack this right from the foundational premise. Because I think we all assume we know what a percent is.
Sure.
We use it to calculate tips at a restaurant. We monitor our phone battery life with it. But I have to ask, is a percent actually a unit of measurement? Like, is it a unit the way a gram or a liter is a unit?
That is the perfect place to start, and the answer is a definitive no. Percent is not a unit of measurement at all.
Wait, really?
Yeah, it's entirely a relationship.
Okay.
The word itself comes from the Latin percentum, which literally translates to by the hundred. So mathematically speaking, converting any fraction or decimal to a percent just means you are rescaling it, so the whole equals 100, like 3/4 becomes 75%.
Right, or 0.09 becomes 9%.
Exactly. But because it is a relationship, it is always defined relative to some base or some whole quantity.
Which means if I just walk into a room and shout 30%, it means absolutely nothing.
It means nothing. Saying 30% is meaningless unless you specify 30% of what, 30% of a pizza is very different from 30% of the national debt.
That is wild to think about because we use that little symbol, the one with the 2 circles and the slash. We use it every single day.
Every day, yeah.
But the concept and that famous symbol actually has this bizarre ancient history. Like, it was born out of taxation and hasty handwriting.
It really was. Percent-style reasoning goes way back.
Yeah.
During the Roman Empire, Emperor Augustus levied this tax called the centesima rerum venalium.
Which was an auction tax, right?
Yeah, it was a 1% tax on goods sold at auction.
Meaning the Romans were already using hundredths as a standard basis for civic calculation?
Yes, but what is fascinating is that the Romans had no mathematical symbol for it. They didn't write a percent sign. They just expressed the entire idea in words.
And here's where it gets really interesting looking at the historical texts we pulled for this. The origin of the actual percent symbol wasn't invented by a single mathematician sitting in some ivory tower.
No, not at all.
It reminds me of how the ampersand symbol, the and sign, evolved from scribes just mushing together the Latin word et. The percent sign is essentially the fossilized remains of a phrase.
That is a beautiful way to visualize it. We know this thanks to historian Florian Cajori's 1928 research on the history of mathematical notation.
Right.
In the 14th and 15th centuries, Renaissance Italian merchants and bankers were, they were desperate for a fast shorthand way to compute interest and currency conversions.
Because they were doing it all by hand.
Exactly. They were writing the words percento constantly in their commercial ledgers.
Just writing it out by hand over and over all day. Percento, percento.
And human nature takes over, so they started abbreviating. Scribes shortened percento, first to pcento, and then even further to pc, with a little elevated o.
Oh, wow.
Yeah, and over centuries of hurried handwriting, that C slowly flattened out into a circle, the P became a slash, and the whole phrase compressed into the percent sign we see today.
That's crazy.
It actually took until the late 17th century for that modern symbol to be standardized in European printed texts.
I love that. It wasn't some calculated mathematical invention. It was just people being tired of writing the same word over and over.
Right, just practical laziness.
But while it started as this commercial shorthand for money, by the 18th and 19th centuries, it evolved. actuaries and economists turned it into a statistical tool for measuring rates of change over time.
Yeah, like tracking life insurance mortality rates or inflation.
Right, but measuring change is exactly where our brains start to betray us.
Because measuring a static proportion like finding a percent of the number is one thing. Measuring percent change requires a formula, and that formula introduces a major trap.
Let's look at the mechanics of that. The formula for percent change is you take the new value, subtract the original value, divide that result by the original value, and then multiply by 100.
Correct. Positive means it increased, negative means it decreased.
But I want to push back on this a little bit. Why must we always divide by the original value? If I'm looking at my new updated exam score or my new bank balance, why can't I just divide the difference by my new number? I care about where I am now.
I hear that, but think of percent change as measuring a journey. To measure a journey accurately, you have to measure from where you started, not where you ended up.
Okay, that makes sense.
That starting point anchors the entire measurement. And for everyone listening who is prepping for their clinical exams, the denominator is the most critical exam-tested detail you will encounter.
The denominator is the anchor.
Exactly. Getting the denominator wrong, like using the new value instead of the starting value, is the single biggest source of errors students make on the math sections of the TEAS and HESI.
Because the denominator anchors the entire calculation, right? So shifting that anchor halfway through a problem leads to deeply counterintuitive results, which brings us to the asymmetry of up and down.
This is the tricky part.
This is where percent math completely defies human intuition. Let me throw a scenario at you, putting ourselves in a clinical setting.
Okay, let's hear it.
Suppose your patient's white blood cell count drops by 50%. Scary, obviously, but thankfully the next day it rises by 50%. Are they back to normal?
Human intuition screams yes. 50 down, 50 up, we should be even.
Right.
But let's walk through the math to prove why that is wrong. Let's say the patient's starting white blood cell count is 100. We'll just leave the specific clinical units aside for simplicity. A 50% decrease of 100 drops the count to 50.
Makes sense. Half of 100 is 50.
But the next day, it rises 50%. You have to calculate that 50% increase on the new baseline. The new baseline is 50. What is 50% of 50? It is 25. So you add that 25 to your baseline of 50, bringing the total to 75.
So they are not back to 100. They are only at 75.
Right. To fully recover from that initial 50% loss, to get from 50 all the way back up to 100, you actually need a 100% gain.
Okay, let me translate this into an analogy. It's like taking $100 to a casino. You lose 50% of your money, so you were down to $50.
A bad night.
Yeah. On your next bet, you win 50% on the money you have left on the table. You just won $25. You are walking out with $75.
Which means you are still down $25 overall.
Exactly. Your baseline shrank, so your gains shrank with it.
That is exactly the mechanism. The base is constantly shifting. And this concept of shifting baselines is why successive changes do not just add together.
Right, the shopping example.
Yes. Think about walking into a store. You see an item marked down 20%, and then there's a sign at the register that says, take an additional 10% off at checkout.
Oh, I fall for this all the time. You immediately assume you're getting a 30% discount.
Most people do. But let's look at a $100 item. 20% off brings the price down to $80.
Okay.
Then that extra 10% off is applied to that new, smaller $80 base. 10% of $80 is $8.
Got it.
So you subtract 8 from 80, bringing the final price to $72.
It is an overall discount of 28%, not 30%. Because percentages cannot just be added or subtracted like regular numbers. Their base is constantly shape-shifting.
Exactly. The base shrinks, so the mathematical impact of the second percentage shrinks along with it.
And when politicians, journalists, or even medical researchers exploit this shape-shifting nature, it leads to the biggest deception of all, the difference between a percent and a percentage point.
This is a crucial distinction, and it is tested heavily in nursing because the implications for patient care and interpreting medical research are massive.
Yeah, we have to talk about this.
We have to separate a percentage, which is a scatic proportion, from a percentage point, which is the raw arithmetic difference between two percentages.
Let's make this concrete with the hospital readmission example from your study notes. Imagine a hospital's readmission rate drops from 20% to 15%.
Okay.
There are two completely different ways to report this exact same reality.
Right. In absolute terms, you just subtract the two raw numbers. 20 minus 15 is 5. So it is a 5 percentage point drop.
Which sounds pretty modest.
It does.
Hmm.
But if you want to report it in relative terms, using our percent change formula, you take the difference, which is 5, and divide that by the original value, which was 20.
Right.
5 divided by 20 is 0.25, or a 25% decrease.
That is mind-blowing. A 5-point drop can be legally, mathematically reported as a 25% decrease in readmissions.
Yes, it can.
Think about how much better 25% decrease sounds in a hospital press release than 5 percentage points. It sounds like a revolution in care.
It sounds massive. And this exact ambiguity is at the heart of a fiercely debated world in evidence-based medicine, which is the relative risk versus absolute risk debate.
This comes up a lot with preventative medications like statin therapy, right?
It does. When a clinical trial reports that a new drug reduces the risk of heart attack by 30%, they're almost always giving you the relative risk reduction.
Okay.
But you always have to ask, 30% of what? What if the baseline absolute risk for a patient was already incredibly low? Say only 1% of patients without the drug ever have a heart attack.
Okay, wait, let me pause you right there. So the baseline risk is just 1%, and the drug cuts that 1% risk by 30%?
Yes. You need to find 30% of 1%. 30% of 1 is 0.3.
Wow.
So the drug lowers the patient's absolute risk by 0.3%, meaning the risk goes from 1% down to 0.7%.
Wait, is 0.7%, as in a fraction of a single percent? I know decimal percentages like that trip up a lot of people on exams.
They do, because it feels abstract. But let's walk through the math on what that 0.3% absolute risk reduction actually means in the real world.
Let's do it.
0.3% means 0.3 out of 100. If we multiply both sides by 10 to get rid of the decimal, that is 3 out of 1,000.
Okay, so out of 1,000 patients, the drug prevents 3 heart attacks.
Exactly. Now, to find out how many people you need to treat to prevent just 1 heart attack, you divide that 1,000 by 3. 1,000 divided by 3 is about 333.
Okay.
In medicine, this is called the number needed to treat, or NNT. You have to treat 333 patients with this drug, exposing all of them to potential side effects and financial costs, just to prevent 1 single heart attack.
So basically, the relative number, the 30% reduction, is the marketing headline. But the absolute number preventing 1 event in 333 people is the fine print.
That is a great way to summarize it. Reporting only the relative figure is mathematically accurate, but it is profoundly misleading to a patient trying to give informed consent.
Which is why health science curricula focus on this so much. It's not just a math trick. It is patient safety.
Absolutely.
And this confusion isn't limited to medicine. Aggregated percentages have historically caused massive misunderstandings in all kinds of data. This is what statisticians call Simpson's paradox, right? The notes mentioned the famous 1973 University of California, Berkeley admissions case.
That is the classic example of Simpson's paradox. If you looked at the university's overall admission numbers that year, the percentage of male applicants admitted was higher than female applicants.
It looked terrible.
It looked like clear-cut systemic bias. But when statisticians broke the data down by individual departments, they found something completely counterintuitive.
What was it?
In almost every single department, women were actually admitted at the same rate or a higher rate than men.
How is that even mathematically possible? How can the individual departments show one thing, but the total average shows the exact opposite?
It comes back to shifting denominators. Women were disproportionately applying to the most competitive departments.
Oh, I see.
Yeah, these were programs with massive numbers of applicants and very low overall admission rates for everybody. Men were applying in higher numbers to departments that were much easier to get into, where the denominator of rejections was much smaller.
So if a highly competitive department rejects almost everyone, and a huge number of women applied there, that massive pool of rejections drags down their overall average.
Yes. When you lump all those different departments with their vastly different baseline acceptance rates into one giant calculation, the aggregate percent tells the exact opposite story of the subgroup percentages that actually compose it.
It's an illusion created by aggregation. You know, it is funny. Wall Street hated this ambiguity so much, they actually invented an entirely new unit to stop the confusion.
They did. They needed a way to talk about changes in interest rates without accidentally losing millions of dollars.
Exactly. Because if an interest rate goes from 5% to 6% and a banker says it increased by 1%, people panic.
Right.
Do you mean it increased by 1% to 5, making it 5.05%? Or do you mean 1 percentage point, making it 6%?
Huge difference.
So finance invented the basis point, which is simply 1/100th of a percentage point. Moving from 5% to 6% is unmistakably a 100 basis point increase. They literally invented new vocabulary to protect their money.
That works for Wall Street. But in healthcare, nurses do not have basis points. They have to use these raw, shape-shifting numbers to protect patients' lives.
Which brings us directly to the clinical floor for you listening. Why are nursing entrance exams like the TEAS and HESI so obsessed with testing this?
Because calculating percent is just one piece of a larger cluster of vital life-saving skills.
Sure.
To be a safe nurse, you have to master ratios, proportions, and dimensional analysis.
Right.
Up percent is fundamentally just a ratio where the second number is always 100. And that specific ratio shows up constantly in IV solutions.
Let's do a concrete clinical application to practice this. A standard normal saline IV bag is labeled 0.9% NaCl.
Which simply means there is 0.9 grams of sodium chloride dissolved in every 100 milliliters of solution.
And a D5W bag, which is 5% dextrose in water, means 5 grams of dextrose per 100 milliliters.
Correct.
So if a nurse hangs a 1,000 milliliter bag of D5W, let me do the math, 1,000 is 10 times 100. So 10 times 5 grams, they're giving exactly 50 grams of dextrose.
That is it. 5% of 1,000 is 50. That is the fundamental mathematical skill of finding a percent of a number just dressed up in clinical language.
Wow.
If a nurse miscalculates a percentage here, they either chronically underdose a patient or they deliver a toxic, potentially lethal overdose. It is a direct threat to patient safety, which is why the exams test it so rigorously.
Before we wrap up, I want to rapid fire 2 final, super common misconceptions to clear up for everyone.
Let's do it.
Misconception 1. Can my patient's medication dose be decreased by 150%?
No. For any positive physical quantity, like a dose of medication, a population of bacteria, or the price of car decreases, are mathematically capped at 100%.
Because that means it's gone.
Exactly. A 100% decrease means you have removed everything, you have reached absolute zero. You cannot have 150% less medication in an IV bag.
And because you can't have negative fluid, however, increases are totally unbounded, right?
Yes, you can increase a dose by 200%, or a population can grow by 500%, but you can only decrease down to zero.
Good rule to remember. Okay, misconception 2. If a clinical study says a treatment has a 75% success rate, does that mean researchers literally tested exactly 100 people and exactly 75 of them succeeded?
No, it does not. And this goes back to our very first point today. Percent is a mathematical rescaling. It is not a literal physical tally.
Right, it's a relationship.
Exactly. If you have a nursing cohort where 18 out of 24 students pass a skills check, that is a 75% pass rate. 18 divided by 24 is 0.75.
So there weren't 100 students.
Right. There were not 100 students in the room. It is just a ratio scaled to a denominator of 100 to make it easier to compare against other groups.
It is just a uniform way to compare apples and oranges. So let's recap our mission here today. If you take nothing else into your exams or your daily life, remember this. Percent is a relationship. It is not a fixed unit of measurement.
Crucial point.
When calculating percent change, always divide by the original starting value, never the new one. Remember, the casino analogy, successive changes multiply. They don't just add together because the base is constantly shrinking or growing.
Right.
And always ask if a medical statistic or even just a news headline is reporting relative risk or absolute risk in percentage points.
If you can master those distinctions, you will not just pass your nursing exams. You will be immune to a lot of the statistical manipulation out there in the world.
Speaking of that shrinking base, I want to leave you with a final thought to mull over. We established that percent changes apply to a constantly shifting base, and successive decreases never simply add up to a clean 100%.
They don't.
So think about how drug half-lives work in the human body. If medication decays by 50% every few hours, it is dropping by 50%, and then 50% of that smaller amount, and then 50% of whatever tiny amount is left.
Continually halving.
Right. If it continually drops by 50% of the remaining base, does the concentration ever mathematically hit a true absolute zero? Or are we all just walking around carrying microscopic, ever-shrinking percentages of every single thing we have ever taken?
Oh, wow. That is a brilliant and slightly unsettling question to end on.
Thanks for joining us for this deep dive. Take these analytical tools, go crush those exams, and we will see you next time.